Hello, and welcome to this Washington State University Extension webinar. In this webinar, which is a companion presentation in a two-part series, we're going to review Approaches to Nutrient Recovery from Dairy Manure, a publication produced by Washington State University Extension. If you're interested in reading the actual publication, that can be accessed online or downloaded as a PDF at the URL listed on the screen. My name is Stacey, and I'm a postdoctoral research associate in the Center for Sustaining Agriculture and Natural Resources. I conduct research primarily focused on the reuse of organically based products in different agricultural systems. Because dairy manure is an organic byproduct, I have an interest in these technologies and the related downstream products. But before I dive into the fascinating world of dairy manure, let me provide you with a quick outline of what this presentation will cover. First, I'll review some background information to provide us some context for the remainder of the presentation. Then I'll touch on the star of the show, manure, by defining it chemically, and then explaining why we're interested in its composition. Following that explanation, I'll describe very generally a few of the ways in which manure is managed today. And then finally, we'll go over some of the newer technologies early in development and commercialization that could be used to recapture the nutrients that are available in manure. Let's begin with our home state. As of 2018, Washington State supported 360 different dairies, which, as you'll see in the map, are distributed across the entire state, though a majority of those dairies are located on the west side of the Cascades. Now, we're not going to delve too deep into the specifics of each and every dairy. Rather, we're going to consider certain general characteristics with regard to all dairies. One way in which the WSDA and the Dairy Nutrient Management Program categorize dairies is by size. These ranges and the resulting size classifications are based upon the total number of milking and dry cows. Small dairies then range from 0 to 199. Medium-sized dairies range from 200 to 699. And large dairies are considered those with anything greater than 700 head. For most of us, milk and cheese and ice cream are the most important dairy products we consider. But for this discussion, what we're really interested in is the manure and the products that can be made from that manure. But let's consider this first. Here are some estimates on manure production for varying classes of cow. In the leftmost column, you'll notice the classification for each type of cow: lactating cow, dry cow, heifer, and calf. Moving to the right hand of the slide, we have mean values in weights, kilograms per day, for each classification of cow that describes information like total manure, which is wet, and then we have 4 columns whose values are figured on dry material that describe total DM, which is total dry matter, and nutrients like N, nitrogen, P, phosphorus, and K, potassium. Important to note here, these values are based upon averages, so there can be quite a bit of variability based upon the size of the cow within each class. In addition to that, these manure outputs can vary based upon diet, time of year, and so on and so forth. At the very least, though, these numbers do provide us with a starting point. One of the first things you'll notice is how drastically the weight drops after a drying procedure. If we focus just on the total manure and total DM columns outlined by the red boxes, we calculate that manure is roughly between 85 and 80% water. If we do a little bit more math, nitrogen is about 5% of the total amount of weight. Hold that idea in your head as we work through some additional math. As an example, let's consider one dry cow. From this one dry cow, we can calculate the amount of manure it can produce over the course of a year, and this allows us to estimate the quantity of material that is produced, and additionally, the quantity of nutrients available for recapture and downstream use. Again, to be clear, we're using average numbers from a per day estimate, and those numbers would likely fluctuate dependent upon the time of year, the feed, and so on and so forth. But again, it does provide us with an estimate. Continuing, we can calculate a rough estimate on the amount of nitrogen in that manure. If we calculate from a dry matter basis, what results is approximately 83 kilograms or 183 pounds of N per year. Let's return to this slide, but only consider a small dairy that has something like 8 lactating, 6 dry, 0 heifers, and 4 calves. We can calculate a rough estimate for the annual amount of N available for recapture. After calculation, that number comes to about 2,008 kilograms or 4,428 pounds of N per year. This estimate, of course, is not accounting for a loss of N due to something like volatilization, nor does it include P, phosphorus, or K, potassium, or other plant macro and micronutrients that may be available in the manure. We're just using the N as a simple example here. So, we have a large quantity of nutrients available to us. That's a good side, but there's also a downside to that as well. To manage these large quantities of manure, the most common approach taken, both historically and today, is field application. This is a strategy where the manure is broadcast and used as a soil amendment for crop production. In many cases, this is managed quite effectively because these systems, including the crops, the soils, and the manure, have been well studied. In certain cases, because dairies have increased in size, matching a crop's nutrient needs to the volume of manure produced has become challenging. What can result is over-amendment or over-application. This causes a release of excess nutrients to the surrounding systems, whether that be air, soil, or water. These, in turn, can cause environmental damage, which is something we're trying to avoid. In addition to that, other challenges exist, like transportation costs. These costs make it difficult to move large volumes of manure to distant fields, particularly wet manure. Also, because manure is a variable material, the nutrient content also varies, making its use as an amendment challenging. With that said, because of technological advancements, particularly in agriculture, additional options and strategies are now available to those managing the vast quantities of dairy manure. But, as is the trend in technology, this field is changing rapidly. What we're covering here is some of the more commonly discussed approaches, meaning this is not an exhaustive list of emerging technologies. For a quick review and to qualify, dairy manure can be handled and managed in several different ways, but for our discussion, and particularly for the nutrient recovery portions, we're going to focus on the manure that is either scraped or washed from a pad, as seen here, and then moved into some type of holding facility. Let's start our story at the beginning, or rather, at the end of the cow. We have raw manure fresh from the cow, and that manure is typically moved to some type of storage, whether that be covered or open. From that storage facility, manure may undergo very little treatment, or it may be anaerobically digested. Anaerobic digestion is a biological process optimized by technology to transform that manure into other products, which means it alters the chemical forms of the nutrients. That's all we'll say about AD, or anaerobic digestion. I just want you all to be aware that it exists. If we continue from the previous slide and follow the material that we have available to us, the manure, we can imagine processing that material through 3 levels of nutrient recovery, each of which can be incorporated into a dairy manure management system. However, not all nutrient recovery technologies will be used in this sequence. Some of the later technologies rely on manure being in certain forms or having certain pre-treatments. For example, anaerobic digestion, which I mentioned previously, preceding the nutrient recovery changes some of the nitrogen from the organic form to the inorganic ammonium form. This can make some technologies more effective but impede others. For an additional example, some technologies rely on fine solids being removed first. So, there are specific needs in some cases for different technologies. But if we take a broad general view, each level extracts varying amounts of nutrients according to the specific technology, and with each level, both engineering and the associated costs are elevated. The first level, outlined in black and identified as Level 1, deals primarily with solid separation, which is more or less a physical operation. I'm going to gloss over advanced solid separation for now, because I'll talk more about that later. The second level of separation, outlined in yellowish green in the upper right corner, are processes that use physical, chemical, and biological transformations to extract even more nutrients. These advanced nutrient separation methods are typically performed following some type of solids removal. Finally, in the lower right-hand corner of the slide, outlined in blue and defined as Level 3, are technologies that further separate solids from the liquid portion, simultaneously creating a highly filtered water that can be used for other purposes. If we move from left to right along the three levels of treatment, we are simply reducing the total amount of volume, fractioning the material into different phases, water or solids, concentrating nutrients while reducing the cost of transportation. Kind of a neat system when you think about it. Now let's take a deeper look at each one of the three treatment levels. At Level 1 of treatment, various types of screens and screw presses are used to separate out large particles and fibrous solids. The diagram on the screen is just an example of one screw press depicting how the material enters, is then pressed by screws and separated into the cake, the solid, and liquor, the liquid. This process can remove between 20 and 40% of total solids and creates a carbon-rich solid, low in N and P, that can be used as a feedstock in compost or as a bedding material. Additionally, after we perform primary solid separation, we can remove even more solids, particularly suspended solids, from the liquid portion. By removing these suspended solids, we can remove an additional 45 to 90% of P, or phosphorus, along with some organic N. These technologies are a bit more advanced, requiring more investment, but generally three approaches are used. Those include centrifuges, flocculation systems, and pressure membrane systems. Each one of these utilizes different technologies to reduce turbidity. Centrifuges generally use gravitational forces to remove suspended solids. Flocculation systems tend to be more diverse, utilizing approaches such as fine mesh vertical screens, belt presses, or dissolved air flotation, also known as DAF. All three, however, depend upon polymers, which are added to promote flocculation and thereby reduce suspended solids. Finally, ultrafiltration is a membrane-based approach that allows water and dissolved solids to pass while filtering out the suspended solids. To reduce clogging, coarse fibers are removed prior to ultrafiltration, and the common design utilizes a cross-flow configuration which increases electrical demand and cost. Now let's move on to Level 2 nutrient recovery. If you'll remember from my earlier slide, I used this little figure to illustrate the second level of nutrient recovery. So far, what we've done with these technologies is 1. Remove solids at Level 1, the primary separation. Then we touched on advanced solid separation, which used the effluent from Level 1 to further reduce the suspended solids using several different approaches. Now, at level 2, we're getting into very specific technologies that are targeting plant-required specific nutrients, N, nitrogen, and P, phosphorus. First, let's deal with N. There are really two approaches to N recovery. NDN, which is nitrification, denitrification, and ammonia stripping. In either case, we're dealing with inorganic forms of N. While we are mentioning nitrification, denitrification here, this type of system is very limited in the animal sector owing to natural biological limitations which impart a relatively high cost to overcome. With that said, one method that does show promise and is likely due to the nitrification-denitrification pathway is vermifiltration. Vermifiltration is a strategy that uses small aerobic bioreactors filled with worms, wood shavings, and other porous media through which liquid manure is treated. Recently, reports have indicated that these systems significantly reduce N concentrations in the effluent liquid while keeping operating and energy costs down, relatively speaking. Research suggests that the nitrification-denitrification pathway is a process contributing to the reduction of N, but much more work is needed to clarify the functional process and its potential for cost-effective N reduction. Ammonia stripping is yet another way to reduce N concentration while reclaiming some of that valuable nutrient. These processes are dependent upon pH and temperature and can be optimized by using air, carbon dioxide air, a vacuum, or membrane and steam stripping. To date, though, and at least with AD treated effluent, the costs associated with this process remain prohibitive for dairy applications. Other inline nutrient recovery technologies will remove some phosphorus, but there is an additional method which removes even more phosphorus, and that is Truebite crystallization. This technology has been successfully used in swine and wastewater treatment, but because dairy effluent has calcium phosphorus precipitates, certain modifications to the process have been made so that a high level of phosphorus capture takes place. For the purposes of our conversation, the phosphorus that is dissolved in the effluent is precipitated as a solid following chemical additions and pH modifications. At the time of our review, only one dairy in the United States was operating a Truebite crystallization device, but nearly 75% of phosphorus is being removed. This technology can be used on dilute manure, manure digestate, or following advanced solid separation. I think it's safe to say that we all appreciate clean drinking water, dairy cows included. The approaches that I'll mention here produce clean water that is suitable as animal drinking water, processed water, or in some cases as discharge water. What makes these technologies an attractive approach is in part due to the cost reduction that results from reducing storage costs. With that said, it is also true that these are generally more expensive, so it's most likely that these would be of interest where hauling costs are high and/or when a dairy is considering the need to build another manure lagoon to handle the volume of manure being produced. There are generally two technologies that produce clean water. They are membrane and evaporation systems. There are many different configurations and materials that can be used in these membranes, but the idea between them remains the same. Particulate matter is removed from a liquid by using force to move that liquid through a semi-permeable membrane as depicted in this diagram. So we have two essential components no matter how those may vary. They are force and filtration. As I mentioned just a few seconds ago, there are a variety of ways to go about this. For example, there are a number of ways to provide a force. Gradients of pressure, concentration, temperature, or electric potential can be used to move the liquid. And there are different sizes for filtration, like microfiltration, ultrafiltration, or reverse osmosis, which removes the smallest particles like dissolved particles and salts. For practical purposes, these systems are used in dairy settings and have been since early 2000s. In addition, this process has been used on both raw and digested raw manure, but when it comes to cost effectiveness, using this technology in step with advanced solid separation has been identified as an important component. When these systems are used in conjunction with advanced solid separation, the output of clean water is between 50 and 70% of the initial volume, where the remaining concentrate still requires field application or storage. And finally, our last technology, evaporation systems. To be clear, this is an idealized diagram as there are many different engineered approaches to this type of technology. But using both thermal and electrical inputs under a vacuum, this process essentially distills and condenses the effluent into clean water. In some cases, pH is adjusted downward to keep ammonium from deionizing into ammonia gas. And primary solid separation is required for this process, but not to the extent of advanced separation. Similarly to the membrane systems, two products result from this technology, a clean water and a condensate, with the systems achieving a similar range of manure volume reduction, roughly 40 to 75% when compared to the membrane system. However, for those that need a high quality water like that required for discharge, additional treatment following evaporation may be required. I know we've gone through an exhaustive list of technologies, but I want to reiterate a point and then I'll sum everything up. One of the most interesting things about these technologies is they can be intertwined with one another in a number of different ways. This allows the dairy manager the flexibility to control costs and to meet their management goals. Some are more appropriately used in sequence with each other, while others are more independent. The set of technologies that might make sense for a given dairy depends strongly on their current manure management costs, including, crucially, whether and how far they are hauling manure, and their goals, meaning which nutrients are of concern and whether or not volume is also a consideration. For example, one could combine primary solid separation and advanced solid separation with a clean water technology, or one could use primary solid separation followed by Truebite crystallization. Clearly, the limitations here revolve around budget and the specific needs of each technology, meaning the type of feedstock. But these new developments do provide a wide range of strategies for dealing with dairy manure. Other than primary solid separation, most of these nutrient recovery technologies are either in the early stages of commercialization or at most are being used at a handful of U.S. dairies. Thus, we expect that as the dairy industry and technology providers gain practical experience with these technologies, costs may change, refinements will be made, and newer approaches will be developed. While we've covered a great deal of information here, we did not cover capital and operating costs. That and some other additional information can be found in the publication from which this presentation is based, and as a reminder, that publication is Approaches to Nutrient Recovery from Dairy Manure, EM112E, which can be accessed at the URL listed on the screen. These technologies are likely to be the most beneficial for nutrient management when they allow for transport of dairy nutrients off the dairy. Thus, one need is to better understand the product or products and their potential use. That information, as mentioned earlier, will be covered in a companion webinar of this two-part series. This activity was funded in part with an applied BioEnergy Research Program internal competitive grant from the Agricultural Research Center at Washington State University's College of Agricultural, Human, and Natural Resource Sciences. Thank you for joining us.